etkinliğimizin son sunuşunu öğleden önce yapacaktım Markus, fakat vakti yetişmedi. Son sunuşumuzu Markus gerçekleştirecek. Stratejik grubu hakkında bazı bilgiler verecek ve sonrasında zaten tekrar sahada demolara devam edeceğiz. Markus, it's your turn.
It's my turn, yes. All my friends are left here. So we have a little bit less people here. I would like to show you a little bit of X-ray diffraction, and prisms, and Parkhausen concepts. But we already got a really nice presentation from Dr. Kemmer of Parkhausen concept theory. So I would like to go more or less directly to the Parkhausen applications. I don't want to do that twice in theory. No, we can do by manually as well. So it's discovered by Professor Parkhausen, but where our machine is based on, it's two doctor theses from Oulu University in Finland, late in 1970, early 1998. I would like to remind you about effect of stress. We already saw that there's a big effect of stress. If you have a compressive stress in your sample, you get a low amplitude. And if you have a tensile stress in your sample, you get a higher amplitude, which means that we get more signal if we have a tensile stress. And here is the same with hardness, that if you have a low hardness, you get a lot of signal, and if you have a high hardness, you get a less signal. And you can see, as we already saw, that this is with hardness, it's a linear. Here is the hardness values in X, and here is the amplitude. So, which means that if we have a low or hard material, we get a lot of signal, and if we have a hard material, we get a very low signal. And for example, hardened components, our goal is that we get the hard material, of course, and we get the compressive stress to our sample, which means that we get a low signal from Parkhausen, because it's very sensitive for both for hardness and for residual stresses. And what happened, for example, if we are already hardened our sample and we grinding, and then we get the grinding burn, it means that we get our hardness is softer, and we get maybe tensile stress, which means that we get again high signal values. That's why we are so good in our field, because our equipment is so sensitive for hardness and residual stress changes. That's why we are in many applications of for example, grinding burn detection. And as you see in here, we have more than 100 different kind of sensors in different applications. Here is our Parkhausen analyzers. We have 3 different Parkhausen analyzers. This Roscan 200, it started to be a quite old one, but it's still useful. Many companies would like to use a Roscan 200 as well. But it's an analog technique. And our newest one is a Roscan 350, and it's a digital technique. And for example, in here there is a picture that our frequency is 100, magnetizing frequency is 125 Hertz, and our analyzing area is 70 to 200 kilohertz. And here we are much more flexible. We can change our analysis frequencies, we can change our magnetization frequencies. And for example, in a production line, everybody would like to collecting somehow data. And we have a ViewScan software that we can collecting our data. And for example, we can have the reaction limit, lower limit and upper limit. And we always should get our signal between that two lanes. If it goes over or under it, then it gives immediately feedback to your production line that there is something wrong. For example, with crying. No, here is our applications, more our applications. And this is one of our product. It's a CamScan 300. It's still white manual that you have to lift it up this sensor and put it to the other places. And here we have a camsets. Here is a little bit more automated camset applications. That this equipment already make measurements automatically. Only you have to load and unload samples somehow. It could be a robot or it could be a user. And this is a fully automated, that there is always robot which loading and unloading samples. And same in crankshaft applications. We have manual stands that operator loading samples, unloading samples, put the sensors to the samples. And you can see that here is a different kind of sensors. Here's the three sensors. One measuring phase and one measuring that load, and one measuring radius of low and phase surface. And here's an automated system of the crankshaft application. And we also have this is a last, let's say, 5-10 years. The gear applications are hot issue. That almost all of gear manufacturers are interested in Parkhausen noise detector. And we are quite flexible because we are still a small company, and we have in our company we have a software department, we have a mechanical department, we have an electrical department, and then we have a sensor department, which means that we are quite flexible with customer cases, that we can do that kind of things quite easily in our house. And of course we have many other applications. Here is for example 3D scan that they would like to measure in 3D scan. Is there any grinding burns? Some shaft scan and so on. Now I have one here. Here's can 500. Oh, you cannot see. can skip that video, but it's really nice. Let's go because we have a quite tight time schedule. Okay, let's go with this one. Sorry, my mistake. Okay, now we can see. So let's go to the X-ray diffraction, because this is a other application. Here I would like to say a couple of words, technique behind of this X-ray diffraction, or theory behind of X-ray diffraction. What we basically have in X-ray diffraction meter, we have to have an X-ray tube and collimator and detectors. And this X-ray diffraction method is based on this law. And what we know of course wavelength, we know diffraction angle. But what we don't know d values between atom planes. So here is a crystal planes, and we have to have a random orientated crystal planes under the collimator. And some of you already saw how this X-ray diffraction works. That we have to use a couple of tilt angles, like Zaim already showed you yesterday. And in first angle we detect the D0 value, then we detect the D1 value, and then D2 value. And you can see from here that our strain direction is this direction, which means that we have a tensile stress in our component, which means also that our atom planes are like this. And if we have a compressive stress in our sample, what we would like to have, it means that these atom planes are almost together, or closer together, than in this D0. And what this means that we have a different distance between a D2 and D0, for example. It means that our diffraction peak shifts. And actually what we're watching is a diffraction peak shifts. Now what we can measuring with X-ray diffraction, we can measuring crystalline materials. And atoms have to be a random orientated. But we cannot measuring, for example, amorphous materials with X-ray diffraction. Some of examples of this kind of materials are glass, for example. And there is some differences if you have a texture in your sample, or if you have a large grain size. There is some difficulties make a measurements with X-ray diffraction. And in our software, how it looks like, here we have a D values which coming from peak shifts. And here we have a shin tube C. And basically that's our tilt angles, but in shin tube C graph. So that angles. And you can see from here when our D values, you can see that it's here something like 0.117, 18 maybe, and here is a 0.11701. It's less in here in tilt angle 45 than in tilt angle 0, it means that we have a compressive stress in our sample. And if we have a, for example, if our D value is 11733, it means in C angle 45, it means that lanes go like this, and it automatically means that we have a tensile stress in our samples. And actually, what we need behind of this calculation, we have to know material parameters, Young's modulus and Poisson principle. And if you don't know that values, it is also possible to measure by four-point bending device, elastic constant device. Here is a G2R in Atılım facilities. This is a other model. This is a portable unit as well. Here we have two different models. This R means that there is a rotation, so we can measure in two different directions. If we have this kind of equipment, we can measure in only the tilting direction. And of course, if we would like to get the results also from this sample to this direction, we have to turn this sample under column. But here you can do that automatically. And this gives much benefits. This is a quite flexible, this express robot system. You can teach in, for example, 100 points, push a play button, and come back after lunch and check what is the results. And you can also measure in really difficult parts or really difficult places that you can put your device like this way or whatever place. Much easier than portable units. It's also possible with portable units, but this is a much more flexible. And this is our white new software. We just saw this graph from our old software. This is a newer one. And there is this software mathematical things based on European standard. Some of applications, here is a floor stand. So if you have, for example, big components, for example, pipe would be a good example, that you put it under the goniometer pipe in here, and you can make measurements from here. Then you can tilt it with this floor stand and make the measurements also from here. And quite often our customers would like to have some kind of capping with X-ray diffractometers. And here is one application from bearing manufacturer that this is a ring stand. That here is our rotation unit, and we have an XY table that we can move under the collimator. That position where we would like to measure, and then we can rotate in that table, and we can measure in two different directions. This is our third method, and Atılım have all of that three methods. They have a Parkhausen noise equipment, they have a X-ray equipment, and then they have a hole drilling prism. And we can see later today, or actually after my presentation, we can see in lab how prism works, how X-ray diffractometer works, and how Röntgen works. Now, principal procedure of hole drilling. For example, X-ray diffractometer, you can measure in quite close of surface residual stress values. For example, in steel, penetration depth with Romy tube and steel is about 5 microns. But with hole drilling, you always have to drill some kind of hole, which means that you cannot get the results from the surface or so close of surface. I don't have a pen. Can I have it? Yeah. So we have to with hole drilling we have to drill a hole, and we have to relieve residual stresses to the sample surface, which means that and we have to take laser images before and after drilling, that we can compare the two sets of images. So what we do, the measured surface displacements are correlated with planar stresses. Here's our drill. It's a high-speed drill. You can run up to 50,000 RPM. Here is a linear or actuator, and they have to be a microposition, because quite often we would like to have a residual stress profile like a 50 micron steps near the surface, that we get enough information, for example, shot peanut samples or whatever. And here is a typical end mills which we are using in here, 1.6 millimeter and 0.8 millimeter. Hole drilling, it's a standard stress measurement technique, and hole depth for prism is limited to 60% of diameter. It's exactly the same with traditional hole drilling, where is a strain gauge system. Which means that if we have a 1.6 millimeter end mill, we can go up to 1 millimeter. If we have a 0.8 millimeter end mill, we can go up to about 0.5 millimeter. And of course, profile depths can be freely chosen. And yesterday was a good question. Good question, that are we comparing the results of X-ray diffraction and hole drilling? Of course we are, because we have both of methods in our house. But I already said yesterday, some of you, that it's not so straightforward, because when we make measurements with hole drilling, for example, this is the first step, 25 microns. With X-ray, we take maybe from the surface, and penetration depth is 5 micron, which means that this is the average values from that first 5 microns. And with hole drilling, this is the average values from first 25 microns. And if we are electropolising 25 microns away, we have a same depth in here. But it's again, when we make a measurement with X-ray, it's average values from next 5 microns. So if you have a deep stress gradient close to your surface, you will get the different values from sample surface. But most of cases it's quite close, and after, let's say, typically after 15 or 25 microns, that results are quite close with both of techniques. Yeah, it's a prism is an optical system. We have to have a central unit, and then we have a camera and illumination stand where we get the illumination light. And we have a laser inside of our central unit. Then we need a prism, scoop it, and then we have a piezo mirror in here. So with prism we can split that laser light with two lanes, and one going to illumination stand, and we get the illumination beam from the stand, and it's going to the camera is here. It's going to the camera, and we have a reference light in here. We put that reference light directly to the camera, and actually what we see, it's a combination of two laser lights. This reference light and illumination light, what we can see. And and of course, what we get here is our sample. So what we get from here, it's a scatter laser light, of course. And what happens when we, yeah, that was what I think. When we drill a hole, we relaxing stresses to the sample surface, which means that we illuminate it with illumination beam, laser light to the sample surface, which means that it's scattered a different way back to the camera, before and after drilling. This is a laser head, and actually we're using a 25 milliwatts purely funded laser nowadays, and we're still using a 532 microns wavelength. And beam is split in this prism scooping. And when I say that we always take a set of images, we take how we controlling with the piezo mirror, and we take a from 90, 0, 90, 180, and 200 wave angles of that images. So here is a camera head. So as I said, that we put two laser lights, reference light and the scatter light from the sample surface to the CCD camera. So why? Some of you already seen yesterday this kind of image in laptop, grouping in Prism Lab. So coherent laser light produces speckle patterns on optical rough surfaces. So we have to have some kind of this kind of surfaces. It cannot be like a mirror, because we don't get any scattered laser light. And of course, the speckle size is affected by the camera aperture. We have an aperture, but which means that you can see in here our speckle sizes, that white and black sizes are some pixels. And if it's a too small, like a 1 pixels, it's a very sensitive for vibration and everything. And if it's too large, you cannot see effect when you release your stresses to the sample surface. You cannot see differences. So it's have to optimize it. Now here I would like to say just that PC is synchronizes phase shifting and frame trapping, as well as we can put the automated imaging drilling. So users just have to given that parameters and then just push a play button and wait the results. And this pre-image, it is took from sample surface. Then we make a hole, and we take a new image sets, and we put all of that 8 images together. We get some kind of phase map, and displacement map. And actually what you see when you make the measurements, you can see that kind of fringes. And interference of light waves scattered from the same surface before and after drilling. So when you see this kind of image in our or video in our laptop, you know that you are releasing stresses, but you cannot say is it a compressive or tensile stress. And we have to have in this video we have to have a pre-image sets and like a live video that we can get to that fringes. So it's a before and after drilling.
So, sorry, what does it mean to dark distances, lambda or truth? Is the wavelength of your laser beam?
Yeah, it is.
Lambda?
Yeah, it is. And why we see that fringes, it's based on Moire patterns. I rather run a little fast. And after measurement, we can put our analysis area. Typically, we're using a 2 times size of hole and 4 times size of hole. So outer limit is 4 times and inner limit is 2 times, which means that we're analyzing this area in here because we cannot see so much changes, for example, after that 4 times hole diameter. And if we put a closer that analysis area of hole, there could be that when we drilling, we always get some drilling chips away. It could be that it scratches that surface, and it's a big effect for results. And of course, we have to have some kind of final element simulation behind the software. It's exactly the same what they have in traditional hole drilling. And again, you have to know material parameters, Young's modulus and Poisson limits. And here is an example values of height and diameter. And here is the same what you can see in maps that if you are just drilled H per D is 0.2 and you have a 100 C stresses, it's this kind of map because you are still quite close on the surface. You are not relaxing so much stresses to the sample surface. And if you are deeper, you have this H per D is 0.6. You can see in map that there's much more stresses are. So basically this residual stress calculation is generate displacement maps from simulation data for each uniaxial stress stage of given H per D. And of course project maps on the sensitivity direction and interpolate for pixel grid. And scale data for Young's modulus and hole diameter. And we have some kind of body movement always when we make a measurements. For example, air movements or these kind of things. We can take care of our calculation, this kind of movements. So we have a correction for rigid body movement. And here you can see a little bit more that here is a experimental phase map, and here is a best fit simulated phase map. So it is to it from that experimental phase map and fit it a little bit better. And here we still have that two analysis, or this is our analysis area, and this example A, it's a measured data, and example or image B, it's a minus rigid body motion of measured data, and this one, this C, is a residuals after subtracting theoretical model, and last one is a theoretical model.
Sorry, this wall is elliptic or because of these sides?
It looks a bit elliptic. Or
It is. Actually, it is because our sample is here, and our camera is here. So what we see is it's coming from here. That's why it's a little bit. But whole should be around. In real life.
due to stress relaxation and
Yeah, yeah, that's true. And measurement parameters, what we have, of course, images, what we are doing. Then we have to know what is our whole diameter that we can do a correct FE, final element model, and whole depth. No, it's coming automatically from software when you give that steps what you would like to use. And this is a good issue in our case that you put that analysis area after that drilling. So when you are drilling the hole, you take a image and you can put it at that analysis area directly up the hole. Because, for example, with strain gauges, sometimes it's a problem. What I remember when I made measurements in university, that sometimes you make a hole, for example, a little bit too close of this strain gauge, which means that it gives quite a lot of error for your results. That you don't get so much strains in these two strain gauges, but you get much more in here, and it's a big effect for your results. Yeah, I have some experimental results, and actually I wanted to take a couple of results where we are compared the X-ray and hole drilling. That X-ray measurements are only done nearby surface, but it's fitting quite well in this case. And this is a shot-peened aluminium, and there is one comment that it's a ghost range. And here I have one more experimental results. You can see shot peening intensity in here, and what happens for residual stresses. If we compare, for example, that our intensity is 0.15, it's this line in here, and we have a intensity 0.35 in shot peening. That effect of that shot peening process is much deeper, so you have a tensile stress much deeper. And if you look at results of these intensities, it's shifting these lines with this direction, that you have a compressive stress deeper in your sample. here we have again some of our customers. So thank you for your attention. And I think that it's not so stressful to make a measurements as you see.
2 tane kısa videomuz var. Demin gösterdim.
Okay. Now we can see one of example. This is a Kierscan 500. So there's a roll scan, and then there's a laptop. There's our ViewScan software, and here's a sensor. First, it's find with laser. You cannot see that laser maybe, but here's a laser light that is indexing that here keys. So find the right position, and it start to make a measurements. Keys. Then it turns a little bit and it's measuring on the other side of other and you can see it's almost impossible to see that values is in there. Now it's and you can see that it's coming up dramatically, which means that if we have a two times more signal, it's absolutely that there is a grinding there. So this kind of Parkhausen equipment, it could be a really simple ones, like a sensor and just a roll scan. Or it could be a sensor, roll scan and view scan. Or it could be a semi-automated or full automated systems. It always depends on cases. And you can see that this is a really portable unit. It's you can do a measurements also on soft floor or wherever you want. The guy have a camshaft and he would like to make some measurements over there. So you can see it. He put it under the collimator, that cam load. This is a safety issue that there is some flex classes, but actually we're using maximum 30 kilovolts and 9 milliamps, or actually one of our tube can use 10 milliamps, but maximum 300 watts, which means that it's a really safety, and it's a safety to operating if you have a safety distance 2 meters between a goniometer and tube, without any safety plexiglasses or anything. So it takes a calibration distance. This machine is already calibrated for powder sampling. And as I said, that you need a few tilt angles. You can get the TV values. Actually, I don't know in this case. I think that it's just from surface.
Derinlik profili değil, sadece yüzeyden ölçüyor.
But with X-ray, it is also possible to make a depth profile by edge. One direction is measured, and now it's measuring other directions. That's fine.
Dinlediğiniz için teşekkür ederiz. Şimdi lablara geçip biraz ölçüm yapmak istiyoruz.